want to talk about arguments to procedures and what they're good for. And the big idea here, it's a little big idea, is generalizing patterns. So up on the screen, we have 4 different procedures for finding the area of various things: a square, a circle, the surface area of a sphere, the area of a hexagon, a regular hexagon. And down at the bottom is an example of, a square of side 6 has area 36, and a circle of radius 6 has area 113 point something. If you look at the actual procedures, you see that there's a pattern. Namely, they're all times something or other, and then radius, or some linear dimension. So it's always some constant times argument squared. These are all functions of one argument, r. But what we can do now is generalize to have a single procedure area that captures this pattern. And the way we do that is we give it a second argument called shape. So the original procedures, like square area, circle area, took one argument. Now we have one single procedure that takes 2 arguments. And so I can say area, square 6, or area circle 6, and get the same answers I got before. But now instead of having 4 procedures, we have 1 procedure. And if I have some new figure that I'd like to be able to find the area of, I want the surface area of a cube, let's say, I don't have to define a new procedure. I just define a new constant. Define cube to be 6 or something. Right? That's the surface area of a cube is 6 times the area of each face. Okay? So that's generalizing patterns. So the idea is we've programmed a bunch of things. We notice that we're writing almost the same procedure over and over again. And we say, OK, I don't want to write the same procedure over and over again, because remember, our job in computer science is to take big, long, complicated computations and make them smaller so that we can handle them in our brains, And one of the ways to do that is to find patterns and generalize them. So now we're going into the second part of the agenda, where we have the idea of adding an argument as a way to generalize a pattern. So the argument that you add is not for the pattern that you're generalizing. The argument that you add is for the thing that's different. Right? So the pattern for those areas was that it's always some number times the square of the argument, the square of the linear dimension. So that's not the extra argument. The extra argument is what's the constant term. And that's what distinguishes a circle from a square, from a hexagon, from a sphere. OK? So now we're going to look at another example like that. Oops. We're looking at 2 procedures that add up terms in a series of numbers. Okay, and the first one is called sum square. And what it does is it gives you the square of the integers, the sum of the squares of the integers between a and b. So if I say sum square 3, 7, that's 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. OK? So let's try that and see what we get. I don't get anything. Why not? Let's try this again. There we go. I got 135, and you can work out for yourself whether that's right or not, because I can't do arithmetic. It's a good thing they invented computers. All right, how does this procedure work? Well, oops, no. Thank you. It's a recursion, like we looked at last week, and it has a base case, like all recursions. In this case, the base case is if A is greater than B. So give me the sum of the squares of all the numbers that are greater than or equal to 8 and less than or equal to 7. Well, there aren't any such numbers, so the sum of all of their squares is 0. So that's the base case. And then the recursive case is, if there are some numbers, let's look at A, which is the smallest of the numbers that we're squaring. And let's go ahead and square that right here, times AA, and add the result of that to a recursive call on sum square A plus 1 B. All right? Easy, right? Any questions about how sum square works? Yes? What if A and B are equal? Okay. Well, if A and B are equal, like for example, let's say sum square 7, 7. So first of all, what should the answer be? 49, right? Because there's only one number between 7 and 7 inclusive, and that's 7. So what the program does says, is 7 greater than 7? No, it isn't. So we come over here and we add two terms. We add 7 times 7, which is the 49, and then sum square 8, 7. So that's the second call to sum square. This time A is greater than B. So sum square 8, 7 is 0 without doing a recursion. And we add that to the 49. We get 49 plus 0 is 49, and that's the answer. Okay? Happy? Yeah. Okay, moving on. Let's do some cube, 3 to 7. And we get a bigger number. We get 775. This is a procedure that computes 3 cubed plus 4 cubed plus 5 cubed and so on. How does it do it? Well, if you look at the code, oops, it's just the same. It says if A is greater than B, that's the base case. We don't have any terms, so the sum is 0. Otherwise, we add two things. The cube of the first number, A times A times A, and a recursive call for A plus 1 to B. Okay? So I could go on with a lot more examples, but I'm not going to. I think you get the point, which is the generalization of this is to be able to add, for any function, the sum from I equals A to B of f of I. That's the pattern that we're generalizing here. Yeah? Only this time, unlike the areas of figures, what goes in this box, the thing that's different each time, isn't just a particular number. Right? So we can't put the square of 3 in here, or the square of 7, or the cube of 3, or whatever, because it's going to be a different set of numbers, A and B, each time. So what has to go in that box, the thing that varies between examples, is now not a number, but rather a function. So that's a big deal, as I was saying, intellectually, in terms of thinking in these terms. But it's not a big deal in programming terms, because in this language, in Scheme, procedures are perfectly good things, just like any other things. So I can now say, define sum from A to B. Nope, I can't. Sum of a function from A to B. So that's the generalizing the pattern. I add an argument for the thing that's different. So what's the same? Well, if greater than AB Oops. Nope. Sorry, let me try that again. Define sum FAB if greater than AB, then the answer is 0. That's the same. If you look at sum square and sum cube and say, well, what part is the same? That's the same. Otherwise, we add two things. That's the same. But now here's what's different. We just call f with a as its argument. So now f is not some particular function. It's whatever function we are given as the argument, as the first argument to sum. Okay, so it's a function f that we're getting as an argument. We can, what is it you do with functions? You call them with arguments. So we're calling whatever f is with the argument a. And the rest of it is the recursive call, sum f, because we have this extra argument, plus a1b. Okay? So that's the same. Now, so let's just stare at this for a moment. Compare the definition of sum on the bottom half of the screen with the definitions of sum square and sum cube. And just as in the area case, sum square and sum cube are almost the same procedure, but we've taken the thing that's different and made it an argument. And that argument is f, the function of a that we have to add into the series. So now to use it, I would have to say something like define square x times xx. And now I can say sum square 3 to 7 and get the answer.